Welcome everyone and good morning. It is Wednesday of week 5, so we're going to go ahead with our recap video. In this video here, I'm going to cover 6 examples. So these first 6 right here. And you can see pretty much they span a lot of the topics that we covered this week, except for there's no optimization questions. So I'm actually going to produce a second video this week, and I'm going to do these 2 optimization questions. I'm just kind of concerned about the length of these videos now. So yeah, in this video, I'm just going to do these first 6 problems, so everything that's, except for optimization. And then in our next video, we'll do examples 7 and 8. And that way, kind of, as you probably suspect, right, there were a lot of people who wanted to see more optimization, at least according to the participation survey. But I still did see, a handful, more or less, in each category, right, who wanted to do areas of rectangles, for instance. So we're going to go ahead and approximate some definite integral using areas of rectangles. Riemann sums came up, so here's a couple of Riemann sums, fundamental theorem of calculus, and using antiderivatives. Here's another one using antiderivatives to evaluate out a definite integral. And then finally, the other version of the fundamental theorem of calculus, right? Basically that derivatives and integrals cancel out, but you have to be a little bit careful with it. It has to be of a certain form. So we will cover all of these things in this video. And then, yes, the second video will do the optimization questions. All right, so without further ado, let's get to it with example number 1. I want to evaluate, or really approximate, this definite integral, right? So this area under the curve of sine of x on the interval from 0 to pi using 4 rectangles of equal width, and then we go on and we're going to do a right-hand sum, an upper sum, and a lower sum. All right, so let's first of all start with A, and we're going to probably use for all of this, the fact that we have this function sine of x, we have 4 rectangles, they have to be equal width, all that sort of stuff. So let's go ahead and maybe figure out what those rectangles look like, and we can draw something that will actually apply to all of these things. So I'm going to go ahead and maybe start off with a number line here. And of course this would go on forever, but I only really care about the piece from 0 to pi in this case. 0 to pi in this case. And if you can even make this a 2-dimensional thing if you'd like. And we know what sine kind of looks like. Maybe I'll draw it in green here. Sine starts off at 0, and then it kind of goes up to 1 at pi over 2. And then it kind of comes back down to 0 at pi. So this is what kind of sine looks like. And again, sine would continue on forever, but we really only care about the piece of it from 0 to pi. So now let's go ahead and break up this interval from 0 to pi into 4 pieces, and those are going to be our 4 rectangles. So we can go ahead and maybe split it in half. So this is going to be pi over 2, and then we can split each one of these in half. So this would be pi over 4, and I suppose this would be 3 pi over 4. More formally, what we're doing here is that we're trying to find this delta x, this width of our rectangles. And according to our formula, this is supposed to be b minus a divided by n. So our b value in this case is pi, that's the upper limit. Our a value is 0 down here, and the number of rectangles that we want is 4. So n is this number of rectangles. And so when you simplify this all down, right, you get pi over 4. So kind of each one of these rectangles should be width pi over 4. And you can see I have successfully done that, right? So this has width pi over 4. 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 So these are going to be my 4 rectangles. Now we need to go ahead and figure out what the heights of these rectangles are. And this is where it really depends. Are you using the right-hand sum? Are you using the upper sum? Are you using the lower sum? But still, we're going to figure out maybe the heights for all of these things. So again, maybe I'll draw it in green here just to do the heights. So the height maybe of this endpoint right here on the left-hand side, that would be 0. And sine of 0 is 0. Next up, if I was to do, at this value right here, pi over 4, and if I want to know what is the sine value there, so sine of pi over 4 is going to be this root 2 over 2. And then sine of pi over 2, that's going to be 1. Sine of 3 pi over 4, that's going to be root 2 over 2. And then finally, sine of pi, that's going to be 0. So now actually we're going to use this picture really for all three parts, A, B, and C. So I went ahead and I've copied and pasted a couple times just so we have a few more copies of this to go ahead and visualize kind of what the right-hand sum is, what the upper sum, what the lower sum, all these sorts of things. So for the right-hand sum, let's go ahead and calculate this. For the right-hand sum, right, we're choosing the right-hand endpoints of each one of these pieces to represent, right, the height of these rectangles. So for instance, for my first piece right here, again, I'm going to be choosing the right-hand endpoint. So this point right here, this is going to be the height of my rectangle. So I can go ahead and maybe draw really quick. This is what my rectangle looks like using a right-hand sum. Okay, for my second piece, my second interval here, again, I'm choosing the right-hand point. So this is going to be the point 1. And so that's going to be the height of my rectangle, and maybe I can go ahead and fill in the rest of my rectangle so it looks something like this. And then for my third piece, right-hand point, that's going to be my height. There we go. And for my fourth piece, well, the height is just going to be 0. So this is quite a boring rectangle. It doesn't have any height really, so its area is going to be 0. So the claim is, right, the area of these three pieces, these rectangles here, can be used to approximate the area under sine of x. So, okay, well, I'll go ahead and shade it like this. So here's sine, and I'm trying to approximate this yellowish area here, and the claim is these blue rectangles will approximate it, right? And maybe it looks like it'd be a bit small or something like this, but I mean, over here, right, I have maybe too much area, and then over here I have not enough, so maybe it kind of balances out a little bit. All right, so now I need to go ahead and calculate out these areas of rectangles. So my first rectangle here, again, the width is going to be pi over 4, and then the height here is going to be root 2 over 2. So that's my first rectangle here taken care of. And again, I'm using the height for the right-hand endpoint, so that's why I get the root 2 over 2. That's the sine of pi over 4. And then the width for all of these is going to be pi over 4. For my second rectangle, let's see, the width again is pi over 4. Remember, they have equal width, so they're going to be the same width for all of them. The height here is going to be 1. So that's coming from this, the right-hand endpoint over here. So that's my second rectangle. For my third rectangle, let's see, we're back down here to a height of root 2 over 2, and the width is still pi over 4. And then finally, for my fourth rectangle, because I mean it says we want to use 4 rectangles, so I won't completely ignore this one. Again, the width is pi over 4, and the height here is going to be 0, though. So that's why it's maybe tempting to not even write this one down. So again, kind of all of them have this width pi over 4, and then they have different heights that are based on the right-hand endpoints. So if I'd like to simplify this, maybe the nicest way I can do this is factoring out this pi over 4, and then root 2 over 2 would be left here, 1 would be left here, root 2 over 2 would be left here, and 0. I guess I don't even need to write that one down. And so let's see, I could combine the like terms, the root 2 over 2. So this is going to be pi over 4 times root 2 plus 1. So that's going to be my final answer here. All right, so that's my answer for A. Let's see how it changes when we're trying to do an upper sum or a lower sum. So an upper sum is going to be, an overestimate. It's going to be too much area, and then the lower sum is going to be an underestimate. It's going to be too little area. So let's go back here, and again, the thing that we're trying to do is approximate the area between sine of x and the x-axis here. So this area right here. And now I want to use an upper sum, so an overestimate. So this is going to be part B here. Very similar thought process. I'm going to go along for each one of my rectangles here. But in this case, instead of choosing either the left-hand endpoint or the right-hand endpoint, I'm going to choose whichever is bigger, right? So it's not going to be a prescribed always do the left or always do the right. It's going to be whichever one's bigger, do that one. Because again, I want an overestimate to give me an upper sum. So, okay. For my first interval here, it looks like the biggest point, kind of if I was writing this function here, the biggest point is over here at root 2 over 2. So that's the biggest one on this piece here. So I'm going to choose that one for the height of my rectangle. So I'm going to choose this rectangle right here. Okay, for my second piece, again, kind of thinking about maybe writing this function a little bit. Looks like the biggest that it ever gets is over here on the very far, the right-hand endpoint. So far, this is basically a right-hand sum, right? Because I've chosen the right-hand endpoint twice. But we can see, actually, this is going to change up here. On my third interval, my third piece, if I go ahead and I write the function, you can see, actually, the biggest that it ever was back here on the left-hand endpoint. So now I'm going to be choosing the left-hand side. And then finally, one last time for our fourth piece, again, kind of thinking about writing this function here, the biggest that it ever was back here on the left-hand side. So it's like sometimes we're doing the right, sometimes we're doing the left. And so in this case, you get a little bit of each. So this is what my 4 rectangles look like in this case. And let's go ahead and calculate out then what the upper sum is. So again, each one of these has a width of pi over 4. So thinking about my first rectangle here, width is pi over 4. And then the height here is going to be this root 2 over 2. For my second rectangle, again, the width is pi over 4, and the height is 1. For my third rectangle, this one right here, again, the width is pi over 4. That's the same for all of them. And then my height is again 1, right? Because I chose this point over here, the left-hand endpoint, because that was the biggest. So I actually double chose 1. But this is allowed when we're doing upper sums and lower sums. And then finally, for my fourth rectangle, again, the width is pi over 4, and the height is going to be root 2 over 2. So that's going to be this one over here. That's what we chose for the height. So again, we're calculating out areas of rectangles. We have length times height, length times height, length times height, length times height, and we add all those areas together in order to give us our total area, right? And this would be the upper sum, too much area in this case for sine of x. Let me go ahead and I'll factor out my pi over 4, and we'll have root 2 over 2 plus 1 plus 1 plus root 2 over 2. And so let's see, pi over 4, again, the root 2 over 2's, those can combine just to a root 2. And the 1's can combine to plus 1, so 2. So that right there is my upper sum. Finally, go ahead and pause the video, I recommend, and try to do the lower sum, part C here. Try to do the lower sum on your own, and then go ahead and unpause it whenever you're ready to see the answer. All right, and there's my answer. I got pi over 4 times root 2. I went ahead and I did the sketch as well. So I have kind of for each one of these pieces, I chose the lower of the two. So I imagine I was writing this function kind of on this piece, and then I chose the lowest, right, for the lower sum, and that was 0 in this case. So that's why I chose a height of 0 for my first one. So there's my 0 for my first one there. And then for the second piece, the smallest that ever was back here at root 2 over 2. So that's why I chose that for my second piece. For my third piece, again, kind of the smallest that it ever got was over here on the right-hand side now, again at root 2 over 2. And then finally on my fourth and final piece, the smallest that it ever got was 0. So I chose that. So always choosing the smallest one. And then my widths were always pi over 4s. So I use, again, we're doing areas of rectangles, so I have to multiply by that width every single time. And then I went ahead and I simplified. All right, so that is example 1. We saw, the right-hand sum, the upper sum, and the lower sum with this, sine of x. Let's go ahead and move on. So this was kind of a 4.1 style question. A 4.2 style question was, maybe can we express this as a Riemann sum, right? So if I wanted to figure out the exact area, right, we'd want to end up using lots and lots of rectangles. So again, kind of the storyline goes here for Riemann sums is that they're again areas of rectangles. So we have widths times heights of rectangles, heights at very specific points here. So we'll use, I don't know exactly what they are, so we'll use x sub i's for the time being. Then we want to add up all of these areas of rectangles. So I'm going to go ahead and use my sigma notation or my sum here to add up all those areas of rectangles. we're going to go ahead and start off with our first rectangle. So at I equals 1 for our first rectangle, and then we'll go to, I don't know, it depends on how many we have. Well, n is the number of rectangles, so I'm just going to use n for the time being. And again, if we want this to be a super accurate estimate, you want to use more rectangles. And so we get the limit as the number of rectangles goes to infinity. And this right here is the Riemann sum, the exact value of this definite integral right here. So in this problem, we don't want to actually evaluate it all the way out. We just want to see, can we express this as a Riemann sum? So let's go ahead and do that. It looks like in order to do this, I'm going to need to know what is my delta x and what is this thing f of x sub I. So let's go ahead with delta x. Remember, we have this formula. It's going to be this b minus a over n. In this case, I know my a value and I know my b value. So we're going to have pi minus a over n, pi minus 0 over n. So that's just going to come down to pi over n. Now remember, when you're doing the 4.1 style, when you're approximating these areas, you have very specific n values. But here, n is actually a variable. It's going to be something where this number of rectangles, this n value, is going to be going to infinity. So I have to leave it just as n for the time being. Now, we need to go ahead and figure out what are these x sub i's. Remember, these are supposed to be the right-hand endpoints that we're using here. So the formula that we have, this x sub I is equal to a plus I delta x's. So we just need to plug in our specific values. So a in our case is 0 plus I, and then that's fine, delta x. So delta x is this pi over n. Oops, that's a 2. Pi over n that we just calculated out here. It's the same delta x as up there. So we can go ahead and simplify this down a little bit. I'm going to write I times pi over n. And finally, right, maybe the last thing is that we don't really want our x of i's so much, but we want the function's value, right, the height. So these are the right-hand endpoints, but I really want the height of our function at these endpoints. So in this case, our function is the sine function. That's back up here. So I'm going to do sine of each one of these values, I times pi over n. So now I have the big pieces here. I have the width and I have the height. So now I can go ahead and plug these things in to get the final answer. So this is going to be equal to the limit as the number of rectangles goes to infinity, summing up those areas of rectangles from I equals 1 to n. And then the widths of these rectangles are going to be pi over n. Remember, in our previous example, n was 4, so that's why we had a bunch of pi over 4s, times the height of the function at these endpoints. So that's going to be this sine of I times pi over n. So this, I've successfully expressed this as a Riemann sum. And then you did also some problems where you had to evaluate out Riemann sums, right? And actually, used your sigma rules and all that sort of stuff to evaluate these things out. But sadly, we don't have any sigma rules for this right here. So this would be quite complicated. So that's why this is just express and it's not actually fully evaluate. All right, that is example number 2, expressing this as a Riemann sum. Now let's go ahead and use the fundamental theorem of calculus to evaluate. So evaluate this. So using the fundamental theorem of calculus, that says, right, if this was some f prime of x here, then this integral would be the same thing as f of b minus f of a. So that's the fundamental theorem of calculus. So this is saying we need to figure out, if this is some derivative function, we need to figure out its antiderivative, right? Where does this come from? And if you can figure that out, then you can plug in b and you can plug in a, and that will give you the true area under the curve. So, okay, we need to play around with this. Well, I remember like cosine, for instance, right? If I started off with f of x equals cosine, if I take the derivative of cosine, it gets pretty close to sine, right? So f prime of x would then be equal to something like sine, but actually it's off by a negative sign, right? So the derivative of cosine is actually negative sine. So in order to fix that, let's go ahead and throw in one extra negative sign here. And then when I take the derivative, we'll have negative negative, so that's going to be the same thing as positive sine. So double check one more time, right? If you take the derivative of negative cosine, you should get positive sine. All right, so now we know what the antiderivative is. I can go ahead and let me rewrite this question here. So the integral from 0 to pi of sine of x dx, we figured out that the antiderivative is negative cosine. And we want to evaluate this from 0 to pi. So this is the whole plug in b, my pi value in this case, and plug in a, that's the 0 in this case. And this is just some notation, right? So let's go ahead and plug in pi. So this is going to be negative cosine of pi. And then we're going to subtract away negative cosine at 0. So, okay, subtract away the negative. That's going to be the same thing as just adding cosine of 0. So, okay, negative cosine of pi. Well, cosine of pi would be negative 1. And then we're adding cosine of 0. Cosine of 0 is 1. So the actual value here is 2. And that's our final answer. The answer is 2 in this case. And so you can see, right, the fundamental theorem of calculus, this is quite powerful stuff. And that's kind of, we were building up to this. So again, the exact area under this curve, if we were to go back to this picture here, this yellow area that we were trying to approximate all those times, this is 2. All right, so with that, let's go ahead and move on to example number 4. Example number 4 is again kind of about these Riemann sums, but now can we go this other direction? So this is some Riemann sum. Again, we have the limit as the number of rectangles goes to infinity, adding up areas of rectangles, and then we have these two pieces right here, and I'd like to kind of go this other direction, right? Can I express this as a definite integral? And we're going to do it when a is equal to 0 and when a is equal to 7 and kind of show how this changes things up a little bit. So, all right. When a is equal to 0, well, let's see. Thinking about what do I need, right? There's usually some widths of rectangles and some heights of rectangles. So let's maybe go ahead and start writing these things down a little bit. I have that delta x would need to be b minus a over n. I know there's this whole x sub I, these right-hand endpoints, and that's supposed to be a plus I times delta x. And really we want some function's value there, so some heights of rectangles. So it's going to be f of x sub I. And I don't know what my function looks like right now, so I really don't know, how to write this quite yet. But let's go back up here really quick and see, all right, maybe is there anything that kind of looks like, and in fact, I know what my a value is here. A is just going to be 0. Oops, kind of switch colors there. So this is going to be b minus 0 over n, or that's just going to be b over n. So the question is there anything that kind of looks like b over n up here that could be one of my widths of rectangles, right? Because it's going to be some heights times some widths, and I kind of have these two different pieces. And so I think actually this is probably going to be my heights. Oops, screwed that up. And I'm thinking this right here is looking a lot like that delta x, the widths of my rectangles. So I'm going to go ahead and choose maybe b is equal to 5 in this case. If b is equal to 5, then this is exactly 5 over n, and those are my widths of my rectangles. So that's looking pretty good. And now we can go ahead, we know a little bit more information here that we can start plugging into these right-hand endpoints. So for instance, I know that a is 0, and I have I times delta x, so that's going to be 5 over n. Now I have exactly what that is. So this is just the same thing as maybe 5i over n. So going back up here, now let's go ahead and maybe start substituting these things in a little bit. I'm going to write the limit as n approaches infinity, the number of rectangles approaches infinity, summing up our areas of rectangles. And let's see, okay, I have 7 plus, and I can see here I have this 5i over n, and that's exactly what my x sub I is, 5i over n. So I'm going to go ahead and put this x sub I, and this all gets cubed, times 5 over n, and that's exactly what my delta x is. So I'm going to go ahead and put delta x. So this bit right here must be what my f of x sub I is. And remember, if I want to express this as a definite integral, I need a few things. My definite integral goes from a to b, and then I have an f of x dx. Well, right now I know that a is 0 and b is 5, but I need to know what f of x is. So in this case, I have my f of x sub I, and if I want f of x, well then just everywhere I see an x sub I, just go ahead and erase this a little bit, and just do x. And so now I know what f of x is. It's 7 plus x cubed. So this Riemann sum right here is trying to get at the area under the curve 7 plus x, all being cubed, on the interval from 0 to 5. So that is my part A. Again, our goal was to express this Riemann sum as a definite integral. And with my definite integrals, we always need an integral from a to b of some function f of x. So let's see how this changes, right? Instead of using a equals 0, if I was to do a equals 7. So if I was to do a equals 7, maybe I'll use this same space here. So if you'd like to keep any of this, I guess go back and screenshot this here, or you can, make sure you have it written down. But I'm going to go ahead and kind of erase things and see how does this change if I do a equals 7. So instead of 0 here, I'm doing 7. And remember, we chose our b value so that it lined up very nicely, and we got this 5 over n. So in this case, we'd have b minus 7. And again, if I want this to be my width here, then I'm not going to choose b equals 5, right? Because if I chose b equals 5, 5 minus 7, this would be negative 2. But I'd like this right here to be my width of my rectangle. So now I have to change what my b value is. So I'm going to go ahead and try out 12, for instance. If I chose b equals 12, notice that I get 12 minus 7, and that's going to be exactly 5. So that's my 5 over n, and that gives me the same kind of 5 over n as my widths of rectangles here. So you have to choose your b value, again, to be kind of distance 5 away from your a value. So before I had 0, so that's why it made sense to do b equals 5. Here I have a equals 7, so now it makes sense to do b equals 12. We also have our x sub i's are changing a little bit. So instead of 0 here, remember now we're going to have 7. That's our a value. And so our x sub i's look like 7 plus 5i over n. So, okay, going down here, seeing how this kind of affects things. Here's my 5i over n. Again, just kind of copying and pasting what I had up here. And notice now the entire thing is my x sub I. So all of this is my x sub I. So maybe instead of just substituting in for this one piece, I have to trade it out for all of this. This is my x sub I. Okay, so the entire function, right, the fact that this is being cubed, that's what's going on, my function in this case. So now if I want f of x, right, instead of just x sub I, I'm going to go ahead and put f of x and just kind of forget about that I for a second. So this is x cubed. So we can see now if I have the interval from 7 to 12, this will just be x cubed. Basically, instead of adding 7 to the x value here, we've added 7 to these the limits of integration. Either way, we'll get the exact same result. If you were to evaluate out these definite integrals, either for part A or for part B, you get the exact same value. So they do represent the same number here. So these are two different ways that you can go ahead and express the Riemann sums. If I'm given an option, I always choose a equals 0, but sometimes it specifies you have to choose a equals something else. All right, that was example number 4. Moving on to example number 5, evaluate out this integral here. The big reason why I choose this problem here is that it's very important to realize that there is no product rule, there is no quotient rule, there are no fancy rules here for antiderivatives. So we're going to be using the fundamental theorem of calculus in order to evaluate out this integral. But unfortunately, right, the fact that we have something complicated on top and something complicated on bottom, right, you'd like to make up like a quotient rule or something like this, but sadly one does not exist, and that antiderivatives in general are quite difficult. And so we have to be careful with these sorts of things. So in order to evaluate this out, really the only thing we have currently is the power rule, or thinking about these antiderivatives. And so the first step is going to be to rewrite this function. So before I even get to the definite integral, I'm just going to pull aside this function here, and I'm going to try to rewrite it so that way it doesn't have this big old division. So maybe one thing that I could do, instead of dividing all of this by u, I could divide each piece. So this is basically just splitting up some common denominator here. And at least for the second piece, we can see there's going to be some good cancellation, right? So the u on bottom can cancel out with one of the u's on top. For this first piece, though, we have this like base, right? It all has base u. And remember, the square root, that's the same thing as being raised to the 1/2 power. So the way that we're going to rewrite this is that there was this good old algebra formula that we had, that if you had these like bases, and I'll go ahead and use a to the b power and a to the c power, that this was the same thing as a to the b minus c power. Oops. And so basically that you can just subtract exponents when you have this division like so. So in my case, right, this is technically u to the first power. I have u to the 1/2 power, subtract away u to the first power. So we have that like bases, they're both u, and then we have different exponents, 1/2 and 1, so we're just going to subtract them there. Technically, that's what you're doing here as well, right? So 2 minus 1 is 1. All right, so minus, and let's see, it looks like 2u there. So this is going to be u to the negative 1/2 minus 2u. So again, all of this was just rewriting this function here, because here it has this division sign and we don't know any quotient rule for antiderivatives. There isn't one, and so we have to go ahead and rewrite it first. So getting in this form here will allow us to take the antiderivative of it. So now let's go ahead and evaluate out the antiderivative from 0 to 9, or the definite integral from 0 to 9 of this function. I'm going to go ahead and substitute in our u to the negative 1/2 minus 2u du. We're integrating with respect to u here. And so for the power rule for antiderivatives, remember it's just the opposite for the power rule for the derivatives. So instead of bringing our power down by 1, we're going to go up by 1. So I'm going to go up from negative 1/2 to positive 1/2. That's because we're doing this antiderivative. And then instead of multiplying by that power, right, we're going to go ahead and divide by it. So I'm going to go ahead and divide by 1/2. Same thing here. So I'm going to go ahead, this is really u to the first power here, and I'm going to raise this up by 1. So u squared, and then I'm going to divide by this exponent. So u squared, so it's going to be divide by 2. And finally, let's go ahead and simplify a little bit. So instead of dividing by 1/2, you're allowed to multiply by the reciprocal, so that would be the same thing as 2. U to the 1/2, that's going to be the square root of u. And then this 2 and this 1/2 will perfectly cancel out, and so we're going to get u squared. Now remember, I have to evaluate this from 0 to 9. So from 0 to 9, did a little bit of simplification there. And by the way, before I even get to this, right, if this was a quiz or an exam or anything where it's really worth some, high stakes points, I would make sure to go ahead and take the derivative of this and make sure you get back to where you started. Right? This should be the antiderivative. So if you take the derivative of it, you should get back to the function that you started with. Now let's go ahead and plug in 0 and 9. I think plugging in 0 won't be so bad, right? The square root of 0 is 0. 0 squared is 0, so that one's nice. 9, on the other hand, well, the square root of 9 is going to be 3, and 9 squared, that's going to be 81. So I get 6 minus 81. And there's minus 0 over there, but that doesn't really matter so much. And so this is going to be negative 75. And that right there is my final answer. All right, one more here, another fundamental theorem of calculus style problem, but this one is to find the derivatives of these functions. And so for this one, we're going to be using the fundamental theorem of calculus part 1. And this part says, right, if you have the integral, so let's go ahead and suppose that you have some f of x here. And this is the integral from any old a value to x of some function, f of t, so it has t's in it maybe, dt. Then, if you want to know what the derivative is, kind of the antiderivative, this integral here, right, because this function now has this integral in it. So if you take the derivative of something that has an antiderivative in it, basically they perfectly cancel out, and you're just left with whatever the function is inside here. But now I guess instead of t's, you would write it with x's, right? So there's just a change of variable. But the derivative and the antiderivative have perfectly canceled out. And that kind of makes sense, right? So let's go ahead and apply this. The problem is, right, you do have to have it in this very specific format, right? You kind of have to have the variable in this top piece. So the problem with my part A here is that my variable is down here in the bottom piece. And so I need to go ahead and swap this. I need to go ahead and make this from 1 to x. Now, the claim is this is not free, right? You can't just go ahead and change this. It actually costs something, right? And we talked a little bit about what this costs in 4.2. And so, right, this is going to be a negative sign, right? In order to flip these around like this will be a negative sign. So again, this is me just rewriting my function, in this case, h of x. So if I want to go ahead and take the derivative, well, the claim is, well, now this negative side is along for the ride. And just the derivative is exactly what's inside of this integral here, now with x's. So this is going to be 1 minus x squared divided by 1 plus x to the 4th, and that is it. It's very tempting. I know you can look at this and say, well, I could take the derivative of that thing, right? I could use the quotient rule on this, but this is actually taking us down, a bad path. This is not actually what we want to do, because our derivative has perfectly canceled out with this antiderivative here. So we've already used up our derivative in canceling that bit there. So if you take another derivative, that's actually the second derivative. So you don't actually want to take the derivative of this inside stuff here. This is one kind of common, temptation that I see students sometimes falling into is, taking the derivative of that inside function, forgetting that they've already used up their derivative. All right, let's go ahead and move on to part B. Part B, we have, okay, we're fine. We have this, nice variable here in the upper limit of integration. So again, maybe I'll just go ahead and rewrite this. F of x is equal to the integral from 3 to x squared cosine of t divided by 1 plus t to the 5th dt. And so you can see this is now more complicated, right? We don't just have x in here, we have x squared. So the question is, well, if I have x squared, how does this influence my answer, right? Can I just apply this same sort of deal here? And the answer is no. You do have to be a little bit more careful with it. So if you would like the derivative in this case, remember we went over and we explained this in the video a bit about why this all works and the chain rule and all that sort of stuff. But basically here we were taking this and we were plugging it in. So everywhere we saw a t, we went ahead and we plugged in an x. So that's what we need to do first of all. So I'm going to write cosine, and instead of just x, I'm going to put x squared everywhere I see a t. So 1 plus x squared to the 5th power there. And then the other bit that we didn't have to do in the first part, and this comes up from the chain rule, is that you have to multiply by the derivative of whatever's up here. So you have to multiply by 2x. So technically we could have done this back here, right? The derivative of x is just 1. So you didn't even have to write this bit down. So you do multiply by the derivative of whatever this upper limit here, the thing with the variables is. So in this case, because we have x squared, its derivative is 2x. And so my final answer in this case, I'd probably write this as 2x cosine of x squared divided by 1 plus x to the 10th power, right? Because we have x squared, and then that gets raised to the 5th power. So this is what my final answer would be. All right, so that is a lot of stuff that we covered in this week. and that you saw in the homework and whatnot from week 5. All the stuff except for optimization. And so we'll have another video that's related to the optimization questions that'll be coming out even later today here. So I hope you enjoyed this video, and I'll send the optimization video in a little while. All right, good luck for your quiz tonight, and I'll see you guys only a week or so away before the final exam, so make sure you're studying. All right, see you guys later.